What quantum computers really do. In the next few minutes, you will understand what a qubit physically is, how its arrows rotate, and why this is more than a coin with randomness attached. In practice, a qubit is always a two-level quantum system. There are many physical realizations, superconducting circuits, trapped ions, neutral atoms, photons. We'll focus on superconducting qubits. They operate the most qubits today. Remember your physics class. A coil and a capacitor together form an oscillating circuit, an electromagnetic swing. Current shuttles between them back and forth, just like a swing moves between its turning points. The frequency is fixed by the components, like a real swing, whose period depends only on the rope length. What varies is the deflection, the amplitude, and the amplitude determines the energy. Classically, this swing can take any amplitude, and therefore any energy, smoothly from tiny to huge. Now we cool the circuit to 10 millikelvin, colder than intergalactic space. The material becomes superconducting. Electrical resistance vanishes entirely. But cold alone is not enough. A normal LC circuit would still have continuous energies even at absolute zero. The actual quantum trick is a component that replaces the ordinary coil, the Josephson junction. Two superconductors separated by a razor-thin insulating layer, only a few atomic layers thick. Josephson predicted in 1962 that bound electron pairs, so-called Cooper pairs, can tunnel through this barrier quantum mechanically. Nobel Prize, 1973 for exactly this prediction. This tunneling makes the oscillation nonlinear. The frequency stays the same, still set by the coil and capacitor. What gets quantized is the amplitude, not the tempo. The system can only oscillate at specific amplitudes, with energies like rungs of a ladder, and these rungs are unequally spaced. That's exactly what we need. Only then can a precise microwave pulse excite the lowest 0 to 1 transition without accidentally triggering the higher rungs. Without Josephson, no qubit. The two lowest rungs are our qubit. Ground state, 0. First excitation, 1. The gap corresponds to a microwave frequency of 5 gigahertz, exactly the frequency we will use to drive the qubit next. Quantum mechanics assigns to each of the two states a complex number called an amplitude. Visually, it's an arrow in a plane. One arrow for 0, one for 1. The length of the arrow squared is the probability of measuring that particular state. Now it gets interesting. If we leave the qubit alone, apply no gate, both arrows rotate, but at different speeds. The rotation frequency equals the energy divided by h bar. The 0 arrow has less energy and rotates slowly. The 1 arrow has more energy and rotates faster. This difference, the energy gap, those 5 gigahertz, is the relative phase we are about to manipulate. Before we compute, we need a defined starting state. So we cool the chip down to a few millikelvin, close to absolute 0, colder than intergalactic space. At that temperature, the qubit is deterministically in the ground state, 0. The 0 arrow has length 1. The 1 arrow exactly 0. From here, the computation begins. Behind the symbol H on a circuit diagram, a concrete physical process takes place. On the chip, an antenna sits next to the qubit. Through this antenna, we send a microwave pulse, 5 gigahertz, exactly the qubit transition frequency, lasting around 20 nanoseconds. This pulse rotates the qubit state by 180 degrees around a diagonal axis. The arrow that previously pointed entirely at 0 becomes 2 arrows of equal length, one at 0, one at 1. This is superposition. The goal, access to the quantum world. Without Hadamard, we would be stuck at classical bit logic. All possible qubit states form a sphere, the Bloch sphere. North pole, pure 0. South pole, pure 1. The equator, a perfect 50-50 superposition with various phases. Every gate is a rotation of this arrow. X rotates 180 degrees around the x-axis. Classical not. Z rotates around the z-axis. It changes the phase without affecting measurement probabilities. Hadamard rotates around a diagonal axis, which tilts the North Pole onto the equator. Here is the proof that a qubit is more than a random coin. Start with 0. First Hadamard. 2 arrows of equal length at 0 and at 1. Now comes the second Hadamard. It rotates both arrows. The 0 arrow splits. Part of it goes to 0, part to 1. Same for the 1 arrow. At 0, both contributions add. Constructive interference. At 1, they point opposite. They cancel. Result. Qubit back exactly at 0, deterministically. A coin, once flipped, cannot return to its origin through a second flip. Amplitudes can, because arrows can cancel each other out. This is the reason quantum computers exist at all. 2 qubits, both in state 0. Hadamard on the first, 50-50 superposition. Now, CNOT. This is a 2-qubit gate. It flips the second qubit exactly when the first is 1, and does nothing otherwise. But the first is in superposition. So the second gets dragged into the superposition with it. The result? A Bell state. Either both qubits are simultaneously 0, or both are simultaneously 1. Never anything in between. They are entangled. Physically, measurement means coupling to the outside world. The arrows collapse onto a single basis state. Which one is random, with probability equal to the arrow's length squared. We measure the Bell state 1,000 times. 50%, 0, 0. 50%, 1, 1. But never a mixed combination. Measure one, you know the other. Instantly. Einstein called this spooky action at a distance, and it has been experimentally confirmed. Now comes the real trick, the biggest misconception first. Quantum computers do not try all possibilities in parallel. A measurement would just return one random answer anyway. The real trick is deliberate interference. 3 qubits, 8 possible states. After 3 Hadamards, all amplitudes are equal. Measuring now would be like rolling a fair 8-sided die. Now the oracle. It knows the right solution and rotates its phase by 180 degrees. The probability hasn't changed yet. The squared magnitudes are the same, but the information is now hidden in the signs. That's the hidden ingredient for the next step. Now, diffusion. Geometrically, it does exactly one thing. It reflects every amplitude about the mean of all amplitudes. The negative amplitude lands far above the mean. It gets dramatically amplified. The other 7 lose height. The solution rises out of the noise. Second round, even more. After 2 oracle diffusion cycles, the solution is measurable with 95% probability. Classically, we would need 4 queries, quantum 2. For a billion entries, classical 500 million, Grover 25,000. And that's only because amplitudes are shaped, not tried in parallel. Classical searches, quantum shapes. That's the core of Shor, of Grover, of every known quantum advantage. Shor's algorithm from 1994, the most famous example. It reduces factoring to period finding and uses the quantum Fourier transform to build, through constructive interference, a sharp peak at the true period. Same principle as in Grover, just with a different shaping tool. All of RSA encryption rests on the fact that factoring classically takes billions of years. A mature quantum computer could do it in hours. Grover's algorithm, 1996. Exactly what we just saw. Oracle flips, diffusion amplifies, repeat. A billion candidates classically. A billion queries. Quantum, about 30,000. Honest intermission. No quantum Excel. No quantum ChatGPT. No 10,000-fold AI speedup. Quantum computers are special-purpose processors for very specific mathematical structures. If you want to see in detail how qubits really rotate, what circuits look like up close, and the Qiskit code behind them, it's all in the blog post. The notebooks run on real IBM hardware. See you next time.